Let's talk about a group of problems called scattering problems. If you look at the one-dimensional potential classically, there's two types of motion you can come up with. The first is bound state motion, and here's an example of that. So here we have a potential, and here's the energy for our little, here it's a little car. And basically these little circle points are the turning points where the energy is equal to the potential energy, and the car without any friction would basically go back and forth between these turning points. That's a bound state. Quantum mechanically, we've talked about bound states in regards to the infinite square well and the simple harmonic oscillator. Another type of motion, classically, is the scattering state motion. And here is where the car can come in from, say, some negative infinity and comes up to some interesting looking potential. And there's two sort of different examples of that here. So here the car comes up, its energy is marked off right here, and basically the potential gets too steep, all right, it has a turning point. The car comes over here again to a point where its potential equals the energy. The car, without any friction, would then just back down and come back in the direction it came. And in the second example, the energy is bigger than the potential, and so the car, even though it'll be going slower here at the top of the hill, it's able to go through the hill. And so this is another type of motion that we're going to have quantum mechanically. And really these two types of motions hook up with the type of experiments we can do. Okay, so bound state, we can put an electron in an infinite square well, or even maybe we can also say put an atom in a bound state together, like a hydrogen atom, and figure out what its hydrogen levels, what its energy levels are. Okay, and so we've talked about our system bound state, getting the energy levels, and we can measure that. Another kind of experiment we can do is shoot particles at something. Okay, and that's similar to the scattering state. We can shoot a particle at something and see, does it bounce back towards us, or does it keep going past the object? And so that's what we're going to be looking at now when we look at scattering states. So let's just look really quickly at the example we're going to do today. And so quantum mechanically, we're going to look at this example of what's called a step. All right, and so we have some particle coming in, so coming in from the left with energy E. It's a scattering problem like we were just sort of talking about, and it approaches a step that has a height of V0. And in this problem, your energy, it's really important, it's less than V0. And we want to know is classically, if this particle came in, what would happen to it? So think about this, and we'll talk about it. All right, hopefully you got that it would hit the barrier and reflect. And basically, classically, this particle comes over here and it doesn't have the energy to get above this step of V0. Now, the thing is it's going to be convenient for us to have this step happening, there's a discontinuity here that's convenient for us mathematically, but in reality, it's not very convenient. And so what this would look like is sort of a step function would look something kind of like this here. Okay, and if we imagine classically our little car coming over, all right, so the energy is right here, so it's just like that picture we had a little ago. The car will come up here to the turning point, okay, where its energy is equal to the potential, and then basically come back again. So classically, this step, even though it's sort of unphysical, what would happen is this particle would hit the barrier and reflect back every time. Now, quantum mechanically, as usual, it may not be certain what's going to happen, but classically, it is certain what's going to happen. Okay, so let's get ready to do our first scattering problem. And here are the steps that we would need to do. So the first step is to divide space into regions. So we're going to talk about how we do that. The second step is to write down the general solution of the time-independent Schrodinger equation in each region. And we're going to try to think about this the way we were sketching wave functions before, about that there's a classically allowed or classically forbidden. So we'll talk about that. And then we're going to basically impose boundary conditions, and there's two boundary conditions. The first one is that our wave function must be finite at positive, negative infinity. And then we're going to have our boundary conditions that at each interface between regions, our wave function and the first derivative of the wave function must be continuous. Once we're done with that, we're going to do the work we need to do, which is to evaluate what our transmission and reflection coefficients are. And we'll talk more about those when we get there. And so let's explain a little bit about this. So the first thing is, again, we have our two basic differential equations. And so all of our potential problems are going to be such that the potential in the region is a constant. And so we're always going to be able to write our differential equations this way, with either negative times some constant times the function. So again, the second derivative equals negative constant times some function, or the second derivative equals positive constant times some function. And again, this one we had listed as the classically allowed regions. Okay, so this is our equation when we're in a classically allowed, and this is our equation, if you remember, when we're in the classically forbidden. And so you can think about it either way. You can think about it as a differential equation, or think about it in terms of the concavity and the classically allowed, the classically forbidden. But either way, when it's allowed, you're going to have the solution that's wave-like. And again, we have the flexibility to use these complex exponentials or our sines and cosines. Be real careful. This should be a negative ikx over here. And then when it's classically forbidden, we're going to have exponential-like functions. All right, and so either way, we can write down what the solutions are just by sort of looking at the situation. And so we're going to talk much more about this, but that's sort of the idea. So here's the first problem we're going to do, scattering problem, and it's the potential step. It's the one we've been describing. So our incoming particles come in from the left, and they hit this step that steps up a potential V sub 0. And we're going to do the case where the energy is less than V sub 0. So there's several cases you can do. And so our first step is to divide this into regions. And so in this case, the regions are going to be right here at x equals to 0. So there's region 1 over here and region 2 over here. And that's our first step. Our second step is to write down the general solution of the time-independent Schrodinger equation. And so that is this clicker question here. So please pause and take a second to do this, and we'll talk about this. Okay, hopefully you got C. And so let's just talk through that real quick. So first of all, our two regions, here is region 1 and here is region 2. And so over here we're classically allowed, over here we're classically forbidden. So right there you know that you should have check sinusoidal solutions in region 1 and exponential solutions in region 2. Now, we didn't have another option like this, so the next question is, okay, so I got that, but where do you get the K's and the L's from? Well, let's see if we can try to explain that. And so here is the case for region 1. So in region 1, we're talking about just on this side here, and so my Schrodinger equation, my potential is 0, so this term goes to 0. And the easiest way for us is to isolate our second derivative. So we isolate the second derivative, and I get negative 2m over h bar squared e times psi. And so the way we generally write that is negative k squared times psi, where our k squared is this constant here. And again, we get the nice sinusoidal solutions. You need both of them. We're going to talk in a second about how you interpret them, but we need to have both as our general solution. Now for region 2, it's a little more complicated because we actually have V sub 0 here for that second term. But it's the same idea. I'm going to try to isolate that second derivative. And so what I do is I take that V0, bring it over here like this. I got negative 2m over h bar squared e minus V sub 0. Now the thing is, because we know that e is less than V0, what I can do is write it this way. And I know that if I write it this way, this thing here will be a positive constant. And so I call this positive constant L squared. This is exactly what we have in that solution on the previous page, 2m over h bar squared V minus E naught. And so I get my second derivative equals positive L squared psi. And so the solutions are the positive exponential e to the Lx, and then plus g e to the negative Lx, just like we said. And this is how you actually get those constants. And so each time you do one of these problems, you'll need to sit down and sort of figure out where these constants come from. All right, so if you're playing along, we've done step 1. We divided everything into regions, 1 and 2, and then we wrote down the general solution of the time-independent Schrodinger equation, and so here it is. Now our third step is to make sure that psi is finite at x is equal to positive or negative infinity. Now this won't always be a problem, but it is a problem in this case. So let's actually, I'll stop here. You guys think about it. Which one of these terms is going to give us a problem at x equals to positive, negative infinity with it going infinite? All right, well, you can see here that these two guys are just sinusoids, and so they're just going to be going on forever, and so they basically are not going to be a problem. However, these two guys, okay, so these are both our exponential solutions in region 2 over here. Well, this one here is going to blow up as x goes to infinity. It's going to get huge. And so this can't be. And so we just get rid of that term completely. And so part 3 will basically only apply when you have exponentials, non-complex exponentials, and basically generally one of them will get crossed out like this. Not all the time, but in this case here, because it is going to be huge at positive infinity. And so we can just get rid of that from our solution completely. So now it's good maybe just to stop and look what we have here and try to think about this conceptually. So what are these equations? What do they really mean to us? Well, we know that e to the ikx's are functions of a constant momentum. And the way this is going to work out is the A is going to be what we call the incoming wave. So it's the one that's coming in to be scattered. And the B is going to be the one that's reflected back, right? Because we know that when it's a positive ikx, it's right moving. When it's a negative ikx, it's left moving. And so whenever we have these scattering problems, we can interpret it that as the A is the incoming, the B is the reflected, and then this G is just going to be sort of the exponential decay tail, something looking like that, into the classically forbidden region. All right, but that's how we're going to interpret these particular pieces. So now you want to set our boundary conditions, step 4, and those are that the psi and psi prime are continuous. So basically that our wave function is smooth and continuous. And so I'll set something like this. So I want psi at x equals to 0 from region 1 to equal psi at x equals to 0 from region 2. And so region 1, so I have a to the I k 0 plus b to the e, it should be negative ik0, and I want that to equal ge to the negative L0. And so what this works out to be is a plus b equals g. So that one works out to be not too bad. Now I want the derivative of psi with respect to x at 0 for region 1 to equal the derivative of psi at 0 from region 2. And so I go through here, and now I got to take the derivatives of these. So it's going to be a, there'll be an ik that comes down from the derivative of that, so e to the ik 0. So again, I got to plug in the 0, and then I'll say negative b times ik, where the negative comes from this ik piece, e to the negative ik 0, and that's going to equal negative gl e to the negative L0. So it's a derivative, so it's an extra step, but still these exponentials come out to be 1, which makes my life a lot easier. And so it's aik minus bik equals negative gl. And so these are the two equations for our boundary conditions that we can go through and solve and finish up this. So now what we're going to find with these problems is that we calculate two parameters, the reflection coefficient and the transmission. The reflection coefficient is going to equal the absolute square of b divided by the absolute square of a. And the rationale here is basically, so these two factors, the a and the b, right? So one gives us the incident, A, B gives us the reflected. And the absolute square tells us the probability of finding that particle there. And so basically, this is the probability of finding B, okay, in that region, divided by the probability of finding A. So it's the reflected divided by the incident. So it sort of tells us how much of the incident is going to be reflected. All right, and then in general what we can do is if we find that, we can say 1 minus r equals the transmission coefficient. And so the reflected gives us a sense of how, it basically gives us a probability. So if we send 100 particles towards this barrier, how many would bounce back? And the transmission would tell us if we sent 100 particles, how many would be transmitted through and go to the other side. All right, and so to solve this, R, we need to find B in terms of A. And so we go to our two equations we just had. So we had A plus B is equal to G, and then IKA minus IKB is equal to negative LG. And what we want to do is we want to calculate B in terms of A so that we can calculate this reflection coefficient or calculate the reflection coefficient. And so I'm going to plug in A plus B over into here for G. And so I'm going to get IKA minus IKB equals negative L A plus B. And so now this is just some algebra. Okay, so for instance, what I'll do is I'll bring all the B stuff onto one side and all the A stuff to the other side. So I get IKA plus L times A equals IKB minus L times B. And if I solve this for B, I can get IK plus L times A all divided by IK negative L. And that's sort of our goal. So now we can take that and calculate the reflection coefficient. And so if we calculate this, so over here if I take B squared, so I'm going to get, so I got to take the absolute square of all of this stuff over here. And so I get negative IK plus L times IK plus L, the absolute square of A, all over negative IK minus L times IK minus L. And of course all of this is just absolute square root of B divided by absolute square root of A. So this is very nice. So these two parts cancel. And what I come out with is K squared plus L squared over K squared plus L squared, which comes out to be 1. And so in this case here, because this step, all right, goes on and on and on basically to infinity, there is no chance that the particle can tunnel through towards infinity. Right, so there is a certain tunneling probability, but if we look at the total reflection coefficient, 100% of our particles will be reflected back at some point. Now Griffiths goes through and does a scattering problem with the Dirac delta function. So you can go over that, and we'll talk more about this next time.